this fourth video, I believe, in chapter 8, where we are going to talk about a really interesting class of reagents that you've never seen before in our class, and we're going to use it to make alcohols. And that new type of reagents are called organometallic reagents. That's kind of the hybrid between organic and inorganic compounds. And so this is where organic chemistry and inorganic, non-organic chemistry intersects. And it might be weird. So this violates one of the things you might have learned in general chemistry, and I just will confess to you as a professor, like we often in your early career classes, science classes, we kind of lie to you so that the material you're learning is easy enough to digest, to simplify things. You might have learned that metals, right, do not form covalent compounds with non-metallic metals don't form these covalent bonds, but that's not exactly true. And so we're going to kind of both apologize and kind of give you the real truth here in this video lecture. Okay, so the two types of reagents we're going to look at are, one is called, this is an example of Grignard reagent, and you might sense something awkward about the pronunciation because that's a French word. It's a French guy that invented this or came up with this reagent first. His name is, I believe, is pronounced Grignard. Often, like undergrad OChem students who might not be paying attention might pronounce this Grignard or something like that, but it's a Grignard reagent. Okay. The other would be simply called organolithium reagent. And I'm here having a phenyl group or benzene group, but this could have been on like a methyl or any alkanes or what have you. Okay, I'm just using that as an example. So how does this work? Well, remember, metals have very low electronegativity. They're very electropositive, meaning they're not that interested in electrons, right? And so for that reason, if you look at the polarity here, this is definitely partially positive, and it's the carbon that's going to have the partial negative charge, which is kind of unusual because so far we've only seen that carbons usually are the one that gets the short end of the stick in terms of electron density when it's attached to other elements like oxygen or halogens that we have seen so far. So here's a very much reversed situation. Okay, and one way to think about these organometallic reagents is you could sort of imagine this bond dissociating, and then if it does, electrons should end up on the carbon side, right? So you could sort of think of this as a carbanion source. Same way with organolithium reagent. And as you can imagine, carbon is not that electronegative, so these anions are very, very reactive. These are very strong base as well as a nucleophile. Okay. So that's what organometallic reagents are, at least we're going to learn in this part of the semester. And so how do you make Grignard reagents? So they could make those actually from some sort of halogen molecules. Okay, so I'm just going to say R group, because the R could be alkyl or aromatic actually a variety of things. And then you mix in magnesium. By the way, X is kind of one way that we describe in generic way a halogen. But in this case, the halogen cannot be fluorine. Then Grignard reagent cannot be formed from it. So it has to be either chlorine, bromine, or iodine. And Grignard reagent is pretty picky and whatnot. The solvent has to be an ether molecule. Okay, so this is the solvent. So typically only either diethyl ether or THF, which remember it looks like that, right? And the reason, part of the reason is once the magnesium inserts itself into this carbon halogen bond, you would form a Grignard reagent that looks like this. But magnesium, because it's feeling the awkwardness of bonded to the carbon and such, it needs to be bonded to other things as well, like the ether. So it actually forms a tetra coordination pattern like this. So I might say that the ether coordination to the magnesium is necessary. So for that reason, the solvent really has to be an ether molecule. And then this, what we're saying, is basically the same as carbanion plus magnesium plus halogen-ish. Technically, there is a bond between all of this. Okay, so that's how you would prepare Grignard reagent. Other examples, you could make phenyl Grignard. Phenyl, the word phenyl just means benzene. So here's a phenyl iodide or iodobenzene. If you add magnesium in THF, this could turn into the phenyl Grignard. Or if you have an alkyl bromide, right? Let's say this would turn into the Grignard reagent. That's how you would make it. Now, how do you make the organolithium reagent? It's very similar. From the halide compound, you just have to add 2 equivalents of lithium. And now I'm going to put this 0 to it to emphasize that this is not a cation, because you need a solvent. But organolithium compounds then are very picky, so this can be any non-product solvent. It could even be like hexane, which is devoid of any functional groups. You could do this in ethers, but it's not very picky. And then you get organolithium reagent, and one lithium gets sort of sacrificed as becoming a salt with the halide, like this. So that's how you would make those guys if you need to make them. And how do you use them to make alcohols? Here's one example. Here we have an ethyl Grignard in ether. Now, I want you to notice what it says here, number 2. That means it's a separate step. Once this reaction, this first step reaction involving all these molecules is complete, then you add water. Because if you add water to this directly, this, remember, is a strong base. You would pick up acidic proton from hydronium ion, and that's all that happens. We would say the Grignard reagent is quenched, would be quenched, and it would not do anything to this ketone molecule. Okay, so this is a separate step after the first step is over. And this is one way that you can abbreviate a benzene ring. So you might might see that from time to time. The product that you're gonna get will actually look like this. Okay, so what's the mechanism? Well, remember that this is basically an anion source, carbanion source, right? So the mechanism should show how this carbon is going to take these 2 electrons and attack electrophilic carbon of the carbonyl. Remember, carbonyl can have resonance structure where the pi electrons are on the oxygen, not the carbon. So we could say this, and then these electrons get kicked up to the oxygen. By the way, this type of a mechanistic step is called nucleophilic addition. Why? Because a nucleophile added to the carbonyl. And the end result, right, is this molecule. And that's the end of the first reaction. Now, in the second reaction, once the proton source is added, this alkoxide can pick up a proton and become that product. By the way, if you're wondering, the counter ion here is magnesium, of course. And we are saying that this is the product of the first step. Okay. You could do a similar thing with organolithium reagent. Maybe I'll think of a somewhat different example. Here's a benzaldehyde. This smells also pretty good. So does this. Acetophenone is a compound that is found in minuscule amounts in like pistachio and whatnot. You can smell the pistachio smell. So if you were to mix these two in, like, say, hexane solvent, and then in the second step you do the acidic aqueous workup. See if you can predict the products based on the mechanism. Pause the video. And that would be the product that we expect. So I kind of did an inconsistent thing. I did the abbreviated benzene ring, but not on this side. So one of the sort of recurring patterns you see is that the organometallic compounds or organometallic reagents, they're very helpful in forming carbon-carbon bonds. Which, as you can imagine, is a very important thing in organic synthesis, because you need to make carbon-carbon bonds to make a new skeleton, new scaffold of a complex molecule that might be useful for whatever reason. So in the final and last video of the chapter, we're going to talk about some pitfalls with organometallics, as well as the idea of synthesizing complex molecules through a strategy called retrosynthetic analysis. We're going to even think about making this complex structure from something that's very simple. Okay, so I'll see you in that video.